power of knowledge, the power of technology. This is you to the power of IBM. Find out how you can do your best work at ibm.com/you.
Get in touch with technology with TechStuff from HowStuffWorks.com.
Hey there, and welcome to Tech Stuff. I am your host, Jonathan Strickland. Joining me in the studio today, our friend Dylan. Hi, Dylan.
Hi.
We're not talking about photo editing today.
We are not.
No, we're talking. Let's do some small talk. How's the weather?
Well, today it is overcast,
Yeah.
and I believe there's a 30% chance of rain.
Yeah, it's a little breezy.
Mm-hmm.
We went up to the roof of the building and reenacted parts of Titanic. I spread my arms and Dylan held me. And I said I was king of the world. And they told me to go back downstairs. No, we're talking about weather, not because I like terrible small talk, although I am adept at it, but because of a listener request. This comes from Dries Sayen. And Dries, I am so sorry if I mispronounced your name. I actually asked Dries how to pronounce this name, and I can only hope I got close. But here's what Dries had to say. Hey, I just wanted to ask/request something about the podcast. See, a while back I had a conversation with my dad. He commented how amazing it was these days. He can just check a website that will pretty accurately tell him whether it's going to rain in the next few hours and where. I said that it doesn't seem like that's amazing progress to me. After all, when he was a kid in the 60s, they would report if it would rain the next day. And now it's just that we've got it down to a few hours instead of 24 hours ahead. He laughed and said the weather report back then was pretty much a joke. Anyway, this gave me a lot to think about, and it seemed like something to learn about from the Tech Stuff podcast. Because to be honest, I have no clue how weather is accurately predicted. It's just always been there for me. So we're going to talk about weather forecasting, meteorology, the technology used to make predictions, what those predictions actually mean. We're going to break all that down. There will probably be at least one or two references to how weather reports are still largely the work of some estimations and best guesses. Because as it turns out, weather's incredibly complicated.
But hopefully, by the end of it, you'll have a little bit more sympathy for meteorologists.
Right. As opposed to my friend who in college wrote an essay explaining what level of hell meteorologists should inhabit based upon Dante's Inferno, which was kind of funny, but also I'm sure meteorologists find it less so. So let's start off with just talking about the history of predicting weather. And really you have to go all the way back to early human civilization, because as it turns out, one of the most important factors that play a part in this is the fact that we humans are pretty good at recognizing patterns. Right? So when something happens over and over, we take note of it and we start to look at the other things that are happening over and over. And then we start to draw some hypotheses. For example, we might think that one thing could cause the next thing, or we might think one thing simply indicates the next thing is going to happen. Here's a simple example. Let's say that you are a shepherd and you notice that the flock of sheep act in a certain odd way every time it's about to rain. You might either come to the conclusion that the sheep are able to sense the rain before it actually happens, and therefore that is an indicator that it's going to rain, or you might come to the conclusion that in fact the sheep are causing it to rain. That's probably not true.
There are two ways to take that, yes.
Yeah, so, but eventually through these observations, you start to eliminate possibilities and you start to draw some conclusions. Now, in early human civilizations, we're talking about very broad conclusions. Things like you notice that in general, the weather gets cooler as the year goes on. You might not even have a year at this point. You may just think, as time passes, the weather gets cooler until it gets really cold. And after it's really cold for a while, it starts to get warm again. And then it gets really warm. And then it gets hot. And then the whole cycle starts over. And you may also notice that the stars, the way the stars are, you can tell that it's a slightly different view as this time goes on. And you start to associate, when the stars get into this, this kind of configuration, it means we're getting toward the time when we should really harvest food, because we're about to go into the winter months, and otherwise we're going to lose everything we've been growing. Or when it's this time, we should start planting food because it's the best time for us to get a big yield later on.
You become attuned to your climate.
Yeah, and you start to figure out, you build out a calendar based on this, and that calendar would be fairly rough. Wouldn't necessarily be reflective of an actual full year, but it would be more like an indicator of what you should be expecting in the next coming time, right? Mm-hmm. So that's your basic, like, big picture stuff. Using things like the way animals react or certain smells that you might detect before a rainstorm. That would be sort of the more acute weather type stuff as opposed to the seasonal type stuff. And you start to draw those conclusions too. And together you start building out general rules that tell you, if this one thing is happening, then here's what you should expect, this sort of pattern recognition. And in fact, today, some of our data still relies on that principle. Mm-hmm. It's just that we have way more information now at a much higher precision than ancient humans did.
And speaking of that, I read that there are certain Aboriginal tribes that have been observing their weather patterns for over 18,000 generations. So that kind of gives you a sense of how far back this goes.
Yeah, and of course, if you're talking about a very specific region, like a very a relatively small geographic area, you could have a pretty accurate idea of what to expect based upon those sorts of observations. Mm-hmm. They might not be presented in the super cool high-tech way that modern meteorology tends to present it, but that doesn't make it any less valid necessarily. Mm-hmm. It may be a little more rough around the edges, but if you can still tell me that, hey, in 3 days we're going to get some rain, and 3 days later it rains, and you do that reliably, that's pretty impressive, right? So, if you want to start looking at people who are really thinking about weather in kind of almost a scientific sense, one of the first people you would have to look at is Aristotle. Big brain Aristotle. He was quite the thinker. He wrote about weather in Meteorologica, and he came up with a bunch of hypotheses. Some call them theories. I would say hypotheses because not all of these prove true. But he came up with some hypotheses about how stuff like rain and hail and wind and clouds and thunder and lightning and hurricanes, what made them happen? How did they behave? What were the rules that governed them? And some of his ideas were mostly right, and some of his ideas were way off. But the problem was, without ways to measure the various metrics associated with weather, it was kind of impossible to say one way or the other. So for about 2,000 years, everyone kind of just went with it because you didn't have any way of proving or disproving any of the individual ideas.
Mm-hmm. But you need a basis.
Yeah, at least it was something. It was at least something to work from. It was just a question of time. When would people develop tools that would allow them to put these ideas to the test and either see which ones are mostly right but maybe need some tweaking, and which ones you can just completely throw out the window. Which brings us up to the Renaissance, one of my favorite time periods, as it turns out. Spend a lot of time there.
Our listeners can't see, but right now Jonathan has a handlebar mustache. A
giant handlebar mustache because the character I play in the Georgia Renaissance Festival has such a mustache, and I will be performing as that character the day after we record this episode. It's opening weekend for the Georgia Renaissance Festival.
Would you say that someone might have a handlebar mustache in the 15th century, around the time of German philosopher Nicholas of Cusa?
It's quite possible. I mean, there's no reason they could not have one. It's not like there were social taboos about such things. So this philosopher, Nicholas of Cusa, designed a device to measure the amount of moisture in the air. And we call these hygrometers. These are, it's really kind of a way of measuring humidity, which here in Atlanta, you can pretty much just say, It's
humid.
It's so humid. Yeah. The humidity in Atlanta is brutal to the point where I have friends who come in from Texas where The temperatures in Texas can get 20 degrees hotter than it gets here in Atlanta. But because Texas has relatively low humidity through most of the state, they think the weather here is way worse, like way more difficult to deal with. But how do you measure that? And he came up with an interesting idea. Now, there's no indication that he ever built the device he came up with, but he said what you do is you take a set of balanced scales. So you know what those look like. They have the little dish on either side. Mm-hmm. And on one side, you put a large amount of wool. And on the other side, you put some weights. He said stones. Other people later on said discs of wax. It didn't really matter. It just had to be a counterweight of some sort. Now, the purpose of the wool is to soak up moisture in the atmosphere, which would make the wool get heavier. This is what Nicholas was saying. Like the wool will get heavier as it soaks up water from the air. And you'll be able to tell that because the scales will start to shift. And you'll see that the side with the wool will start to get heavier. Then if it dries out, if the weather gets dry, the wool will start to lose moisture. It'll evaporate, and you'll start to see that side of the scale moving up. It'll get lighter. Now, he never built that, but another big thinker of the Renaissance did get around to it, Leonardo da Vinci.
Yes, I mean, he did everything.
Yeah. When he wasn't building helicopters or designing tanks, which he never built, but he did design. He designed a tank, and he designed a really weird, I think, it was something like a 33-barrel gun.
Didn't he, I think, a diving suit as well?
Pretty much any sort of thing that in the Renaissance would sound like it's science fiction, Da Vinci had some sort of hand in.
He probably has a primitive tablet schematic somewhere.
Yeah. He probably at one point came out to his patrons and showed a wooden slate and talked about how if you ran your fingers across it, you could paginate through, and then he'd say, I think you're gonna love it, and then maybe even did a one more thing. So that was the first kind of weather-related instrument that people were really thinking about. Another would come in the 17th century, early 1600s, usually put around 1603, when physicist Galileo Galilei created a thermoscope, which is sort of a predecessor to a thermometer. And it was a pretty simple idea. So you start with a container that has a small amount of liquid in it, usually water. That's your base. And then you also have a kind of a hollow tube of glass that ends in a bulb. So like a larger bulb at one end and open on the other end. And you could do something like warm the bulb if you wanted to in your hands, but then you would put the bulb, you would put the tube into the small container of water. The bulb would be suspended above it. Usually the hollow straw-like tube would be long enough, several inches long. You could then observe that as the temperature of the bulb changed, the level of water in the tube would either go up or go down. And this is because the air inside the tube is either expanding or contracting, depending upon whether it's heating up or cooling down.
And this wasn't a thermometer, but it was interesting, and it was once again a start.
Yeah. Later on, someone looked at Galileo's little invention and said, what if we put like markings on the tube so you could say how many steps up or down the tube it went? Then we could even give indications of how much warmer or cooler it got. You could say, it's 4 steps warmer or 4 steps cooler. That became the basis of the thermometer. So, and that didn't take long. It was within about 50 years that you had the first working thermometers following this kind of proof of concept thermoscope. There is the Galilean thermometer. Are you familiar with these?
I am not.
You've probably seen one. They are these cylindrical glass. They're usually very decorative for like a home office desk or something. But they're these glass tubes. They are cylindrical typically. Inside they have these little blown glass balls that contain their own liquid. Often it's a liquid that has dye in it, so they're blue or green or red or whatever. And each one has a little weight attached to it that has a temperature. And what happens is the balls represent different densities of water, and the temperature of the glass tube will change the density of the water inside the glass tube. And then you'll see whichever ball is at the bottommost of the tube, the glass tube is, that represents the general temperature. And they tend to be between like about 5 degrees apart. So you might have 65 degrees, 70, 75 degrees, 80, that kind of thing. So whichever one's at the lowest point, that's the temperature of the water, thus the temperature of the area surrounding it. They tend to be used, like I said, as decorations for desks and stuff. Galileo actually did not invent that, but some of his students did. It was several of his students, so that's why it's called a Galilean thermometer.
Well, that's pretty neat.
Yeah. It's a very pretty way of seeing, generally speaking, what temperature the tube is, and therefore probably what temperature the surrounding air is. Keeping in mind that water changes temperature more slowly than something like a room would, so it wouldn't be reflected immediately. But it's still kind of interesting.
Hey everybody, it's Chuck from Stuff You Should Know here to talk to you a little bit about my brand new podcast called Movie Crush. It is where I sit down with your favorite people to talk about their favorite movie, and I'm telling you, I've been having a lot of fun with this show. The Movie Crush community online has been killing it on Facebook, and if you want to hear people like John Hodgman, Tig Notaro, Kevin Pollak, Paul F. Tompkins, Janet Varney, author John Ronson, if you want to hear all of them talk with me about their general movie-going fandom history and their favorite movie, check out Movie Crush, releases every Friday at Apple Podcast or wherever you get your podcasts.
Then we have the barometer. This is a very important tool in predicting the weather. So barometer is all about predicting, or not predicting, but measuring atmospheric pressure. So first thing, just in case you weren't aware, the atmosphere exerts pressure on us. It pushes down. Gravity is technically pulling down on the atmosphere. So the lower you are to the surface of the earth, like the lower down in elevation you are, the more pressure you feel from atmosphere. This is why as you climb a mountain or you get on a plane, you experience lower amounts of air pressure. It's also why you have to pressurize aircraft that fly at pretty high altitudes. Otherwise, you would suffer some pretty rough effects.
Mm-hmm. And on the Earth's surface, the force of gravity, due to the force of gravity, the pressure is about 14.7 pounds per square inch.
Yeah.
That's at sea level.
Yeah, that's what we call an atmosphere of pressure, right? 1 atmosphere of pressure. You look at it at sea level. Specifically, you're looking at it at sea level at 59 degrees Fahrenheit, which is 15 degrees Celsius. You have to be very specific because temperature will change pressure. As you warm up air, typically, this is just a general rule of thumb. When something warms up, that means molecules are moving. That's the energy of motion. Ultimately, you're making these molecules move faster, and that's kind of what heat looks like. So as molecules of air move around more, they spread out more, it becomes less dense. So that would change the atmospheric pressure as well. That's why you have to take temperature into account when you talk about 1 atmosphere of pressure. It's very specific. It's at sea level, at that temperature, that's 1 atmosphere. So that's kind of interesting. Anyway, the first person to actually create a barometer was a guy by the name of Evangelista Torricelli. And his first invention people just called Torricelli's tube, which doesn't seem very dignified.
No, it needs a special name.
Yeah, but Torricelli's tube, it wasn't quite the barometer yet. What he was doing was he was actually experimenting with the concept of vacuums, like creating a vacuum within a tube or some other container. It was one of those things where we didn't fully understand what that was, how it worked. And so he did this experiment. He was actually friends with Galileo, and Galileo said, "Hey, Evangelista, I got an idea for you. Why don't you take one of those tubes you've been working with and fill it with mercury and use that in your vacuum experiments? It'll be a lot easier to see than some other liquid." And Torricelli says, "All right, I'll give it a shot." So he took a 4-foot long glass tube and he filled the glass tube with mercury. So it was closed on one end, open on the other. And then he inverted the tube into a dish, and the dish had a little bit of mercury at the bottom of it. And it showed that despite the fact that the top of the tube, like the mercury went all the way up this 4-foot tube, the liquid didn't just come rushing out and spill everywhere, right? Because the vacuum is what held it in place. And he says, "Look, see, I was so smart. This shows that there's something working here. We're going to really explore this." But then he noticed something else that was really interesting. He noticed that despite the fact that the tube could stay upright and the liquid would stay in there, from day to day, there were variations in how high the mercury would be in the tube. And it wasn't just sinking down. It's not like it was leaking over the course of a week. So like you come back and it's a couple inches lower, and then the next day it's a couple inches lower. It wasn't like that. Some days it was actually higher. And he started thinking, well, what the heck would cause the mercury to go up or down this tube?
The atmosphere.
That's it. The atmospheric pressure pressing down on the liquid in the dish. That's what determined whether that's what determined the height of the mercury inside the tube. So on days with higher atmospheric pressure, it pushes down on that exposed liquid within the dish, and it forces that liquid to go up the tube, and so the height of the liquid inside the tube goes up. On days where atmospheric pressure is lower, some of that liquid comes down and starts filling up the dish until it reaches that kind of equilibrium. And then he said, hey, this shows that the atmosphere itself exerts pressure, and not only that, but the pressure is not consistent day to day. It can change. And in 1644, Torricelli built the first mercury barometer. So now he was building something specifically to measure this thing, because before he was really demonstrating the concept of vacuums. So now we've got the barometer, we've got the thermometer, we've got the hygrometer.
So essential things.
Yeah, these are the basics for taking measurements about weather. And at that point, it was really the start of gathering enough information so that meteorology, the science of meteorology, could actually exist, right? Because now we could not just observe patterns, we could actually quantify what was happening. And by quantifying it, we could get to this level of precision where we could start to draw more specific conclusions as to what would or would not happen based upon current conditions. So, all that being said, we still have some issues predicting weather. So why is that? Well, like I said before, it's complicated. So, here's the thing. Our atmosphere is fluid. It's a gas, but it behaves via fluid dynamics. Dylan, have you ever studied fluid dynamics?
I don't believe so.
Oh, I studied them in physics, and they are brutally difficult to comprehend because it can get there's so many factors that can affect a fluid. So, and the Earth has a whole bunch of them happening at once, right? First of all, there's this big ball of plasma that's about 8.5 light minutes away from us. It's called the sun.
I've heard.
Yeah. On nice days, you might even get a glimpse of it. So the sun provides obviously a ton of energy to the Earth. And so the Earth absorbs a lot of solar radiation, and that can affect fluid dynamics because you've got a lot of heat coming into a system. On top of that, you've got the Earth. The Earth's not standing still. The Earth is rotating. That rotational force creates other fluidic effects in the atmosphere. We'll talk about those specifically when we get to high and low pressure systems. You've got gravity, which is pulling down on the fluid. So that's another force that's in play. You've got differences in surface temperature on the Earth. So you've got areas where it's very cold versus areas that are very hot. That in turn affects the atmosphere and can change things around. You have air currents, a big deal there. That's also partially due to the rotation of the Earth. You've got mountain ranges, which can act as like a windbreaker for certain things. That changes the way weather patterns happen. Lots of things that are all in play.
And some of these are localized and some can concern large portions, like air movement.
Oh, yeah. Yeah. Some of them are some of the effects of these can be felt hundreds of miles from where the thing happened, right? Which makes it even harder because, as a layperson, you sit there and think, all right, well, because I can't see any clouds on the horizon, I think tonight's going to be all right. And then you could have a very fast moving system coming in due to something that happens well out of sight. It ends up creating a lot of things that could be counterintuitive depending upon what you have at your disposal. Like, of course, the more information you have, the better conclusions you can draw in general, assuming that you also know what you're talking about. So let's talk about some of these things, these different major components that shape weather, like atmospheric pressure. So we just talked about that with barometers, but what does that mean? So what is happening? Well, I talked about how you have warm air that has air moving around a lot. That means it ends up spreading out. It becomes less dense than cold air. You probably have heard the phrase that warm air rises and cold air sinks. Mm-hmm. That's not entirely accurate as to what's going on. What's really happening is cold air is more dense than warm air. So cold air comes to take up the space that warm air had, which forces warm air to go up. So it's not so simple as warm air rises, cold air sinks. It's more like, if you've got these big, heavy weights at the top, then they're going to come, they want, quote unquote, want. There's no desire, but they have a tendency to move downward, forcing the lighter stuff to go upward. That's pretty much what's happening here. So, when you're talking about our atmosphere, you have to keep in mind it's three-dimensional. It's not on a flat plane. That's easy to forget when we look at weather reports because we're looking typically at a flat map, right? That has a bunch of stuff, like it's got little flags all over it and little lines around it and H's and L's, and you're wondering what, maybe there's some clouds in there too. But typically you're looking at a two-dimensional representation. But really you have to remember that weather is a three-dimensional phenomenon. Mm-hmm. So that makes it a little more complicated. Also, you got to remember the water cycle. So cold air can't hold on to moisture the way warm air can. All right. When you have warm air, and it's close to the surface, let's say you've got some nice warm, moist air close to the surface of the planet, and cold air is sinking down, forcing the warm air up. As the warm air rises, it's going to start to cool. And as it cools, it can no longer hold on to the moisture that it had, which means the moisture starts to condense. Water vapor begins to condense. This is how you get clouds and ultimately how you get stuff like precipitation. So, understanding that's important. So now let's imagine way up in the atmosphere at the top level of where our weather happens. We have these massive air currents. Now, in cases where air currents are converging together, so you've got two air currents that are meeting up, they start to force air out of the way. Now, air can't go any further up.
It has to go down.
It has to go down. That's the only place to go. So that air coming down increases air pressure at that location. You have air moving down toward the surface of the earth, pushing down. Your air pressure goes up. So an area of high pressure, you know what kind of weather you typically see in an area of high pressure?
Clear, dry weather.
Yes, exactly. So when you have a high pressure system, it's typically pushing the moisture out of the way. It tends, and we have to use phrases like tends or words like tends because it's not every case is equal, but it tends to be cooler. It tends to be sunny. It tends to have less wind than low pressure systems. So this high pressure system creates pleasant weather. Low pressure systems are different. Oh, and also if you were to view this from the sky, like you're above this high pressure system, and if you could see air, first of all, that would be a nightmare. But if you could, you would see that the air's not just coming down like a column. It's not like you turn on a spigot of water and water just falls straight down. It's actually turning as the air is sinking, right? As this high pressure system forces air downward. And it actually moves in a clockwise direction, which is funny because I was looking at Dylan a second ago and making a twisting motion, but I was doing counterclockwise. But no, it moves in a clockwise direction. This is, by the way, due to the rotational force of the Earth, in part. So you've got this rotating clockwise system that's pushing air downward. That's your high pressure.
Hey, I'm Jack, host of the new comedic news and pop culture podcast, The Daily Zeitgeist from How Stuff Works. little bit about me. I've listened to almost every episode of Stuff You Should Know and Stuff You Missed in History Class. I'm the co-founder and was the editor-in-chief of Cracked for the last 11 years. And our show is basically the day's news and pop culture filtered through a brain that contains all the information that entails.
And I'm Miles Gray, Jack's co-host, a former political operative and pop culture addict, like something I actually take medication for.
He does. And sometimes he's a bunch of different people, like Michael McDonald.
Tell him he's a stranger.
A Japanese radio DJ.
皆さんおはようございます。マイルスです。
And Making a Murderer's Brendan Dassey.
Yeah. No.
Just a fair warning, guys, you're going to learn a lot, but some of the content can get a little edgy, so not for young ears, but trust us, it's all in good fun. So go to Apple Podcasts and listen and subscribe to the Daily Zeitgeist. It's really good, is our catchphrase. We're still working on it.
So that's your nice weather. Low pressure, I think you can probably take a wild guess. It's gonna mean...
crummy weather.
Yeah. This is where you're getting clouds and rain, and typically you're talking about air being pulled upward. So why is air getting pulled upward? Well, remember I was talking about those currents up in the upper atmosphere where they were converging together and forcing air downward? If the currents are moving apart from each other, if they're diverging, they create sort of a vacuum effect over that region. And that starts to pull air upward, creating an area of low pressure. Warm air from the surface gets pulled upward. It starts to cool down and the water vapor condenses. That's where you start getting those overcast days, the cloudiness, the rain. On top of that, you're creating, since it's a low pressure system, you're creating the opportunity for some pretty hefty winds to move in. Right? Because air is always going to move from an area of high pressure to an area of low pressure. That's just pure fluid dynamics. It makes a lot of sense. If you've got, imagine that you have two water balloons connected to each other. All right? Mm-hmm. And they are in equilibrium. So they're equally full. Not totally full, but equally full. If you're to squeeze one of those, creating an area of high pressure, it forces the water to go to the area of relatively lower pressure, right? You're forcing water into that second water balloon. Same thing is true with low pressure systems. You've got a low pressure area. That means any area around it that has higher pressure, air is going to want to move into the area of lower pressure. That's where you get winds coming in. And it can get pretty breezy. So this one, if you were to look overhead and view the air, it would be rotating in a counterclockwise or Widdershins, if you are Shakespearean, direction. And the air would be coming into the low pressure system as opposed to coming out. Like in high pressure, it would all be moving outward in that clockwise direction, with low pressure inward in a counterclockwise direction. Now, the reason why I even bring this up is because it's important to understand how high pressure and low pressure affect weather. So things like the wind speed, the potential for precipitation or lack of precipitation, all of those would play a part. And it's important for you to know what the pressure is of that region in order for you to make any sort of forecast. So the barometers would be the tools you would use to get those measurements. Now, the old style barometers, the mercury ones, use fluid to indicate changes in pressure, sort of like what we were talking about with Evangelista's barometer, simply just looking to see where the level is. So area of high pressure pushes the liquid further up. You would say that pressure is rising and weather is probably going to be pretty nice. In fact, if you ever have seen one of those old school barometers, it probably has like a little drawing of sunshine toward the top of it where the level goes up. If the glass is falling, if the mercury is going down the tube, then that would suggest low pressure, which suggests cloudy, nasty weather. But we also have other types of barometers. In fact, not a lot of people use the mercury ones anymore. Don't know if you know this, Dylan.
Mercury is not the best thing to use.
It's a little toxic.
Yeah.
It'll drive you crazy. You'll go mad as a hatter. They're also aneroid barometers, which were invented in the 19th century, 1800s in other words. These have a tiny little metal box, and the sides are all made out of a flexible metal, and changes in pressure either push the sides of the box inward or allow the sides of the box to flex outward. That in turn is connected to tiny little levers which are connected to a needle. And then you look at your device. It can look like a little stopwatch actually. And you see where the needle is, and that tells you where the atmospheric pressure is at, right? Or you could use digital barometers, which have little pressure-sensitive transducers that essentially do the same thing. They're just doing it with a transducer as opposed to an actual physical metal box. And how do we talk about these measurements? Well, it depends upon what system you're looking at. But typically weathermen, meteorologists, I should say weather people, I suppose.
That sounds like a good term, yeah.
Yeah, weather people.
An inclusive term.
Yeah, meteorologist is probably more accurate, but they tend to use millibars to describe atmospheric pressure.
But in the U.S.
Here in the U.S., we sometimes refer to inches of mercury because, darn it, we like that system. The standard scientific unit is the Pascal, or PA. And then there is, of course, the 1 atmospheric pressure type approach. That's not terribly useful if you're talking about tiny changes in atmospheric pressure. Like, yeah, it's a 0.0006 atmosphere change. Doesn't help you very much. To me, it's kind of like measuring temperatures in Celsius. It works great if you're boiling water. But if you're doing anything else, Celsius to me is it's too brute force an approach to describing
All I do is boil water, so that's perfect.
Right. That's just really whenever I go by Dylan's desk. It's just a pot of boiling water and some photos on his screen, and that's about it. So then we have temperature and moisture. Those are the other two really big components. So a large body of air that has a similar temperature and moisture throughout that body of air is called an air mass. So when two air masses are near one another, they are separated by a thing called a front, right? So you've heard of cold fronts and warm fronts, obviously, right? Mm-hmm. So we'll focus on the United States. We have 4 major types of air masses that affect our weather here in the United States. This is not the way it is everywhere. These are the 4 that in general affect our weather. So you've got continental polar air masses.
Cold and dry.
Yep. Continental tropical air masses.
Hot and dry.
Yes. Which, by the way, only happen in the summer and come up from Central America.
That makes sense.
Yeah. Then you have maritime polar.
Cool and moist.
Yeah. And boy, I'm so sorry for you people out there who hate the word moist. And then maritime tropical.
Warm and moist. There it is again.
Yeah. So your continental polar air masses, those tend to come from our friends to the north, Canada. Mm-hmm. They ship us their poutine, their Tim Hortons coffee, and their continental polar air masses.
Don't bring up Tim Hortons. I'm still bummed that there's not one here.
I'm actually still look, Canada, I poke a lot of fun, but I fully admit Tim Hortons is a phenomenal chain.
A national treasure.
I would welcome it with open arms to come here to Atlanta. Just throwing it out there. Your continental tropical, like I said, comes up through Central America and typically only affects our weather in the summer. Maritime polar, that tends to come from the far northeast. So we're talking like in New England, that area. Maritime tropical, pretty much everywhere else. And by tropical, when we say hot or warm and moist, we don't necessarily mean like it feels like you're in the Caribbean. It just means not cold, right? So the fronts tell us what sort of air is moving into an area. So a warm front, first of all, they tend to move pretty slowly. Warm fronts are not known for moving through an area quickly. And they bring lots of rain because warm fronts are pushing out cold air. So imagine you've got a mass of cold air in an area. A warm front is coming in. That warm air, when it encounters the cold air that's already in that region, the warm air's inclination is to kind of go up the cold air like a ramp. Because again, the cold air is more dense, right? So the warm air can't just push it out of the way. The warm air is less dense than the cold air. But it can start to go up on top of it, which means the warm air starts to cool down.
And condense.
Exactly. And that's why we get rain at the edge of a warm front. So they move pretty slowly because warm air just doesn't push cold air out very efficiently. And we get a lot of precipitation. Cold fronts where cold air replaces warm air, move faster and tend to have intense but short thunderstorms and other precipitation as the front moves in, and the weather tends to clear up pretty shortly thereafter. The reason for this is, imagine you've got a mass of cold air moving in. You have warm air in the region. The cold air is going to almost act like a shovel, scooping up that warm air, pushing it up into the upper levels of the atmosphere, of the lower level of the atmosphere, but the upper side of it, which cools that air down very quickly. Because of that quick cooling, you get things like bigger rainstorms, thunderstorms, but they tend to happen very quickly. And then once the front has moved through, things are okay again. Spend a summer in Atlanta and you will see this phenomenon repeatedly, right? Like there are times where if it's a particularly humid month, you might be able to set your watch by when the thunderstorm is going to come through.
You'll see extreme versions of it as well. Not disaster level, but you'll see quick, intense thunderstorms with hail and heavy rains, and they'll be gone in an hour or two.
Yep. And then it just becomes a steam bath for the city.
That's Atlanta most of the time.
Yeah, but it's particularly bad about an hour after a thunderstorm. It's probably the most miserable Atlanta feels, right? Because it's like walking into a steam room.
Yes.
So again, the reason for that fast, violent weather is just the speed at which that warm air is being pushed up and cooled down so that it can no longer hold on to all this moisture that was once part of it. And it has to go somewhere. So it lands on us. So that's kind of interesting. There are also stationary fronts. Stationary fronts are when two fronts just kind of collide and that's it. They're just there. And it's going to stick around for a while. You'll have a lot of rain, typically.
Sounds like the traffic jam of fronts.
Yeah. And then there's occluded fronts, and that's when a warm front gets caught between two cooler air masses. So the warm front gets pushed up, and we get a lot of intense thunderstorms with occluded fronts, too. Dylan and I had a lot more to say about weather. As it turns out, it's pretty complicated stuff if you hadn't picked up on that already. And so in order to preserve your sanity and ours, we've decided to split this episode up into two after we had recorded the whole thing. So make sure you tune in to next week's episode for the thrilling conclusion about how weather technology works and what all of those predictions actually mean. Because we dive into that and explain how the meteorologists put together things like weather forecasts. And it was a really fun experience to talk about all of that. In the meantime, if you have any suggestions for future episodes of Tech Stuff, or maybe there's someone you would love to have on the show as a guest interview or guest host, let me know. My email address is techstuff@howstuffworks.com. Or drop me a line on Twitter or Facebook. The handle at both of those is TechStuff, HSW. And I'll talk to you again really soon.
For more on this and thousands of other topics, visit howstuffworks.com.
Hi, this is John Roderick from the rock band The Long Winters.
And I'm Ken Jennings from the syndicated quiz show Jeopardy!
We have a podcast called Omnibus.
It's a time capsule of our era, and we put a new entry in the ground every Tuesday and Thursday.
Listen on Apple Podcasts or wherever you get your podcasts, and subscribe to never miss a single episode.